Welcome students to the lecture number 13 for the MOOCs course on fuzzy sets, arithmetic and logic. In today's lecture, we shall study some additional properties of alpha cuts. If you remember, we have already seen some properties. Say for example, alpha plus cut of A is contained in alpha cut of A for all alpha for a fuzzy set A defined on some universal set X. Another property that we have been using is that if alpha is less than beta, then beta cut of A is contained in alpha cut of A. Today, we examine some more properties of alpha cuts. So, let me first state 4 results. Let A and B be 2 fuzzy sets defined over a universal set X, then for all alpha belonging to the interval 0, 1, we have A is contained in B if and only if alpha cut of A is contained in alpha cut of B for all alpha belonging to 0, 1. B, A is contained in B if and only if alpha plus cut of A is contained in alpha plus cut of B for all alpha. C, A is equal to B if and only if alpha cut of A is equal to alpha cut of B for all alpha, and D, A is equal to B if and only if alpha plus cut of A is equal to alpha plus cut of B for all alpha. So, let me prove these results. A is contained in B if and only if alpha cut of A is contained in alpha cut of B for all alpha belonging to 0, 1. Proof. What do you mean by A is contained in B? Since A is contained in B, we have membership of X in the set A is less than equal to membership of X in the set B for all X belonging to the universal set X. Now, suppose A is contained in B. we need to show that alpha cut of A is contained in alpha cut of B for all alpha belonging to 0, 1. Suppose, if possible, alpha cut of A is not contained in alpha cut of B, implies there exists x such that x belongs to alpha cut of A, but x does not belong to alpha cut of B, implies membership of that x in A is greater than equal to alpha, but membership of x in to the set B is less than alpha, contradicts that mu A of x is less than equal to mu B of x for all x. So, this is very obvious from this side that if A is contained in B, then alpha cut of A is contained in alpha cut of B. Conversely, suppose alpha cut of A is contained in alpha cut of B, we need to show that for all x belonging to x, mu A of x is less than equal to mu B of x. Suppose, if possible, there exists x naught such that mu A of x naught is greater than mu B of x naught. Let mu A of x naught be alpha and mu B of x naught be beta. Therefore, by assumption, alpha is greater than beta. Since we have mu A of x naught is greater than mu B of x naught. Therefore, x naught belongs to alpha cut of A, but since mu B of x naught is equal to beta, which is less than alpha, therefore, x naught does not belong to alpha cut of B. Therefore, contradicts that alpha cut of A is contained in alpha cut of B, and this contradiction arises because of the assumption that there exists such an x naught. Therefore, we can see that mu a x is less than equal to mu b x. For all x implies A is contained in B. Proved. Now, let us prove B. B suggests that A is contained in B if and only if alpha plus cut of A is contained in alpha plus cut of B for all alpha belonging to 0, 1. Again, as before, let A contained in B, suppose if possible alpha plus cut of A is not contained in alpha plus cut of B, implies there exists x naught such that x naught belongs to alpha plus cut of A, but x naught does not belong to alpha plus cut of B, implies mu A of x naught is strictly greater than alpha, but mu B of x naught is less than equal to alpha. So, together contradicts that A is contained in B. Why is the contradiction? We assume that alpha plus cut of A is not contained in alpha plus cut of B. Therefore, we prove that actually alpha plus cut of A is contained in alpha plus cut of B. Conversely, suppose alpha plus cut of A is contained in alpha plus cut of B for all alpha, we need to show that A is contained in B. Suppose not. That means there exists x naught such that membership of A of x naught is greater than membership of B of x naught. Only in that case we can say that A is not contained in B. Now, let mu A x naught is equal to alpha and mu B of x naught is equal to beta. Therefore, alpha minus beta, let us call it epsilon, and this is greater than 0. Consider alpha prime is equal to beta plus epsilon by 2. Therefore, since mu a of x naught is equal to alpha greater than alpha prime, therefore, x naught belongs to alpha prime plus cut of a. But since mu b of x naught is equal to beta, which is less than alpha prime, therefore, x naught does not belong to alpha prime cut of b. So, this contradicts our assumption that alpha plus cut of a is contained in alpha plus cut of b for all alpha. Therefore, this contradicts the assumption that alpha plus cut of a is contained in alpha plus cut of b for all alpha. Therefore, we conclude that A is contained in B. Let us now look at statement number C, which says that A is equal to B if and only if alpha cut of A is equal to alpha cut of B. Proof: suppose A is equal to B, that is, for all x belonging to x, mu A of x is equal to mu B of x. Suppose, if possible, alpha cut of A is not equal to alpha cut of B, implies there exists x naught such that x naught belongs to alpha cut of A, but x naught does not belong to alpha cut of B, or conversely. That is, there may be x naught which belongs to alpha cut of B, but that does not belong to alpha cut of A, but the line of argument is going to be very similar. Since x naught belongs to alpha cut of A, but x naught does not belong to alpha cut of B, this implies that membership of A of x naught is greater than equal to alpha, but membership B of x naught is less than alpha. This contradicts the assumption that fuzzy set A is equal to fuzzy set B. Therefore, we conclude that alpha cut of A is equal to alpha cut of B. Conversely, suppose alpha cut of A is equal to alpha cut of B, we need to show that A is equal to B, and I forgot to mention that for all alpha belonging to 0, 1. It is not only one alpha or a finite number of alpha, it is for all alpha belonging to 0, 1, this assumption holds. We need to show that A is equal to B. Suppose not, then there exists x such that mu A x is not equal to mu B of x. Let mu A of x is equal to alpha, mu B of x is equal to beta, and without loss of generality, let alpha be greater than beta. Therefore, x belongs to alpha cut of A, but x does not belong to alpha cut of B, because membership of x to the set B is equal to beta, which is less than alpha. This contradicts that alpha cut of A is equal to alpha cut of B. Hence, we prove that if alpha cut of A is equal to alpha cut of B, then for all alpha, then mu A of x is equal to mu B of x for all x, or A is equal to B if and only if alpha cut of A is equal to alpha cut of B for all alpha. Statement D is very similar, and I leave it as an exercise. Okay, students, we have already seen the following properties with respect to alpha cuts. One, alpha cut of A intersection B is equal to alpha cut of A intersection alpha cut of B, alpha cut of A union B is equal to alpha cut of A union alpha cut of B, alpha plus cut of A intersection B is equal to alpha plus cut of A intersection alpha plus cut of B, and 4 alpha plus cut of A union B is equal to alpha plus cut of A union alpha plus cut of B. These results we have already seen, and perhaps it is not difficult to imagine that we can now extend it to finite number of sets as well. Question is, what about similar results when the number is infinite, or in other words, that is, let A I be a sequence of fuzzy sets defined on a universal set X, where I is equal to 1, 2, 3 up to infinity. That means, we are now looking at an infinite collection of fuzzy sets defined over the same universal set X. Question is, what is the relationship between alpha cut of AIs and alpha cut of their unions, intersections? So, we need to study this when we are looking at an infinite number of sets A1, A2, A3, etc. So, the theorem A union over alpha cut of AI is contained in alpha cut of union over AI. So, with respect to two fuzzy sets, we have seen that they are actually equal, but in this case we find that it is a containment. The union of the alpha cut of the individual AIs is contained in the alpha cut of the union over all the AIs. But with respect to intersection, we find that the result is intersection over I of alpha cut of AI is equal to alpha cut of intersection over I of AI. The third result is union over alpha plus cut of AI is actually is equal to alpha plus cutoff union over I A I, and fourth result is alpha plus cutoff intersection over A I is contained in alpha plus intersection of alpha plus cutoff A I. These are all intersections is over the entire sequence of sets A1, A2, A3 up to An. Thus, we can see that there is a difference when we are looking at only two sets and when we are looking at infinitely many sets. In these two cases, we find that the equality does not hold, rather it is a containment. Question is, why so? This happens because when we work on finitely many sets, then mu union over A I, say I is equal to 1 to n of x, is defined as maximum over I mu A I of x. When the number of sets is finite, this maximum can be defined, but when we have infinitely many sets, then we cannot define maximum. It is replaced with supremum. Similarly, for intersection, minimum is replaced with infimum. And because of this, we see that the equality does not hold for all the cases. So, with that small insight, let us now start proving these results. So, the first result is union over I alpha cut of A I is contained in alpha cut of union over I A I. Proof. Suppose x belongs to union over I alpha cut of A I. Implies there exists I naught such that x belongs to alpha cut of A of I naught implies membership of x to the set A I naught is greater than equal to alpha. Therefore, supremum over I mu A I x is greater than equal to alpha. Therefore, x belongs to alpha cutoff union over I A I. Therefore, we prove that if x belongs to this union, then x belongs to alpha cutoff union over A I. Therefore, this is surely contained in this. But why the containment comes? We need to show there may exist x in this which does not belong to union over I alpha cutoff A I. Let us now show that if x belongs to alpha cutoff union over I A I, then it is not necessary that x belongs to union over I alpha cutoff A I. Consider the following. Suppose for all x belonging to x, mu A I of x is equal to 1 minus 1 upon I. What does it mean? That is, mu A 1 of x is equal to 0, mu A 2 of x is equal to half, mu A 3 of x is equal to 2/3, like that. Therefore, supremum over I mu A I of x is equal to 1, because supremum over I of 1 minus 1 upon I is equal to 1. Therefore, x belongs to 1 cutoff union over I A I. Because the supremum is 1, therefore, membership value of x to the set union over I A I is equal to 1. Therefore, x belongs to the 1 cutoff union over A I. But since mu A I over x is equal to 1 minus 1 upon I, mu A I over x is strictly less than 1 for all I. Therefore, 1 cutoff A I is equal to phi for all I. What does it mean? It means that here in this case x belongs to 1 cutoff union over I of A I, but 1 cut of A I is equal to phi for all of them. Therefore, x does not belong to 1 cut of A I for any I. Therefore, x does not belong to union over I of 1 cut of I. Therefore, union over I 1 A I is strictly contained in 1 cut of union over I of A I. Proved. So, this proves the result that union over I of alpha cut of A I is contained in alpha cut of union over A I. Let us now prove the second result. Intersection over I alpha cut of A I is equal to alpha cut of intersection over I of A I. So, in this case we can see that there exists strict equality. What does it mean? It means that if we take any x belonging to this set, we will prove that it belongs to this as well, and similarly if I take an x belonging to this set, we will show that it belongs to this. Suppose x belongs to intersection over I of alpha cut of A I, implies x belongs to alpha cut of A I for all I, implies mu A I of x is greater than equal to alpha for all I, implies infimum over I of mu A I of x is greater than equal to alpha. This is because since each one of them is greater than equal to alpha, its infimum is also greater than equal to alpha, implies x belongs to alpha cut of intersection of I of A I, because the membership of x to the set intersection over all A I is infimum over mu A of x I. Right. So, once we assume this, we prove that x belongs to the alpha cut of intersection over all A I. Conversely, suppose x belongs to alpha cut of intersection over I of A I, implies infimum over I mu A I of x is greater than equal to alpha, implies mu A I of x is greater than equal to alpha for all I, implies x belongs to alpha cut of A I for all I, implies x belongs to intersection of alpha cut of A I. Therefore, this and this are same. So, this proves result B. So, we proved result B also. In a similar way, one can prove result C. I leave it as an exercise, but what I prove now is result D. So, result D is the following. It shows that alpha plus of intersection over I A I is contained in intersection over I of alpha plus of A I. Note that here it is strict containment. Proof: first we show that this one is contained in this. Let x belongs to alpha plus cut of intersection over I A I implies mu of intersection over I of A I of x is greater than alpha, strictly greater than alpha, because it is alpha plus, implies infimum over I mu A I of x is strictly greater than alpha. Since the infimum is strictly greater than alpha, it implies that mu A I of x is strictly greater than alpha for all I, because if it is not strictly greater than for some I, then infimum cannot be greater than alpha. Implies x belongs to alpha plus cut of A I for all I. Since x belongs to alpha plus cut of all A I, this implies that x belongs to intersection over I of alpha plus cut of A I. Therefore, we assume this and we prove that x belongs to alpha plus cut of A I. Now, let us look at the other way around. Now, consider the following example. Let mu A I of x is equal to, say, half if I is equal to 1, and it is 1 upon I if I is greater than 1. Therefore, x belongs to 0 plus cut of A I for all I. Therefore, x belongs to intersection over I 0 plus cut of A I. However, infimum over I of mu a I of x is equal to infimum over all these terms half, 1 by 3, 1 by 4, etc., which is equal to 0. Therefore, membership of x to the intersection of a I is equal to 0. Therefore, x does not belong to 0 plus cut off intersection over I a I. Therefore, we see a case that x belongs to this, but x does not belong to alpha plus cut off intersection of a I. So, this proves the result. Okay, friends, I stop here today. In the next class, I shall look into alpha cuts and strong alpha cuts. We will see how these can be used to represent a fuzzy set. Okay? Thank you so much.